Okay, so let's get started. It's 2:30. Okay, so this class we're going to finish up some flow, some more applications of flow, and I guess like this is the last, the last few applications are pretty cool, and then we'll talk about one more way to find maximum flow where the running time doesn't depend on this big F. Okay. All right. So, yeah, and then yeah, I guess one thing I have to say is like, yeah, maybe on the exams, right, the type of questions about flow you'll be asked, it won't really be about the proofs of flows. It'll be more like kind of like these applications. I give you a problem, and then you have to reimagine it as a flow problem, right, and solve it. So in that sense, like the last part in the second half of the class, it's not going to be so important, but still pretty cool to see the new ideas that are used in the, in how to actually find a flow without having this F dependency. Okay. So let's get started. Yeah. So I'll briefly mention this in the notion, and then actually we'll see way more of this in about like 2 weeks. So basically, right, like whenever we see an application of flow, that means we're actually doing a reduction. So what does a reduction mean? Basically, it means like problem A is in disguise. Like problem A is essentially problem B in disguise. Okay, so when we say problem A reduces to problem B, like you might hear, just when we talk about things in general, like say, oh, well, I don't know if people talk like that anymore, but essentially when we say problem A reduces to problem B, that just means A is a special case of B, okay? So, or stated in other words, if I can solve problem B, then I can solve problem A, okay? So, for instance, I might say, finding the max element reduces to sorting because, sorting is a harder problem, right? Like if I can solve sorting, then I can find the maximum element, okay? So that's all that means. And the only reason I'm introducing this terminology is like, we're going to see it in the slides. Like in some of the applications of flow that we have left, it's going to be like, oh, this problem reduces to flow. It's a special case of flow. Okay, so let's get started. It's like, for example, right, maximum matching reduces to flow from last time, because to solve maximum matching, right, we turn it into a flow problem. Okay. So now let's get started. So now we'll see like much harder problem, but it's actually a flow in disguise. So it's going to be called circulations with demands. And here, as we'll see, like it's not even clear. So it's going to be like a flow problem, but with a lot more constraints. And it's not even about finding the maximum flow now. It's about finding any feasible flow. Okay, like any feasible solution to the constraints. Okay. So what is this problem? Now we don't have a source and a sink, right? Like previously in flow, source had like infinite amount of stuff. Sink could handle infinite amount, it could intake infinite amount of things. We just had to send the maximum amount of stuff from the source to the sink. But now the problem is a little bit different. Now we have, let's say, factories, right? Every factory has like some amount of stuff, a finite amount of stuff. And we have like consumers, and they each have like some amount of stuff that they want, okay? And we want to say, okay, we want to route all the stuff from the factories to the appropriate consumers, okay? So let's see that in a concrete example. So the green nodes have supplies. So the reason these numbers are negative is because we can just think of everything as like having every node like demands a certain amount. So if something has supply, that's just minus demand, okay? So just a convenient way to talk about everything without having two terms. Okay, so everything has a demand, and so we can represent these supplies of factories as minus demand. Okay. So now the problem is this. Okay, so we have these green factories. They have some amount of stuff. Okay, so the first factory has 4 units of things, and the second factory has 7, and they must they must transport their things on this graph. And now there are these red nodes, okay? These red nodes you can think of as like the the phi node destination. So for instance, this red node says, I need 3 units of stuff to end up here, okay, to end up at this node. And this other red node says, oh, well, I need 8 units of stuff. All these other nodes, they don't have any demand, meaning like they just act as, just intermediate stages of, stuff flowing through them. Okay, so the goal is the following. I want to send all the green stuff to the, I want to send from the green nodes to the red nodes. And I still have these edge capacities. And for every other node, I want to employ, I want to ensure that the flow is conserved, okay? So for all these white nodes, flow in must equal flow out. Only for the red nodes can I have excess flow, okay? Does the setup of the problem make sense? Like we just want to transport stuff from the green nodes to the red nodes while respecting the, the amount of stuff that can go on any edge. And for every other node that's not a red or a green node, flow in has to equal flow out, okay? Does that make sense? So you can think, right, like red nodes are, green nodes have their factories with things. Red nodes are like people that want to consume things. And the green nodes are just like, let's say, intermediate storage, right, that you can pass stuff through. But at the end of the day, right, they can't create things and they can't hoard any things, okay? Does that make sense? So here, right, there is no max flow problem, right? Like I'm not sending as much stuff from a source to sink. I know how much stuff I want to send. Actually, the hard part is even finding a way to send things, right? It's like any feasible flow. So it's not clear, right? So previously, right, in the standard flow problems, a feasible flow was just not send anything, a flow of 0. That was pretty, that satisfied all the edge constraints, right? Here, here the constraint is, right, I have stuff I want to send. The green nodes have to send, for instance, this green node has to send is like 4 units of stuff somewhere. And the red node, it doesn't care. At the end of the day, it has to get 3 units of stuff, okay? So it's like a more complicated flow problem because even finding any like feasible flow is not so clear, okay? So does the setup of the problem make sense? Questions? Okay, so any idea how to turn this into a max flow problem? Like a standard flow problem that we saw before. So previously, we need a source and a sink. Here, it's like not so clear, right? Source and sink are, but any idea? Yeah. Sorry, can you say that again? Yeah, so that's a interesting idea. But the thing is, right, somehow this 8 units of stuff, it can't all come from one thing, right? It has to come from both. Yeah. So actually, the transfer, like, if I just told you this problem, like, it seems very, very complicated. But actually, it's another max flow problem in disguise. So, right, so let me just formally define the problem, right? We have the same capacity constraints, right, for every edge. At most, the capacity can travel on the edge. But now we have these demand constraints, right? Every vertex says, I need some amount of stuff to, I need the flow to leave some amount of stuff inside me. So for instance, for the white nodes, the demand is 0. I don't want anything here. For the green nodes, the demand is negative, right? Because they need to send stuff out. And for the red nodes, the demand is positive. They need to end up with stuff at the end of the day, okay? So this is just a formalization of the problem, okay? And right, just to make that point clear, right, there's no maximum quantity here. I just want to find any flow, any feasible flow, okay? And sending 0 is not a feasible flow here because, right, these have negative demands. I need to send things out, okay? All right. So first, right, there is a sanity check to do, which is, well, if the sum of the green is not equal to sum of the red, then this is not possible, right? Like, right, the fact that there's 7 plus 4 here, and there's 8 plus 3, and they add up to the same number, that's important, right? Otherwise, someone is going to be, not happy, right? That's something. All right, so yeah, so like I was saying, we're going to turn this seemingly more complicated problem into just like a trivial application of max flow, okay? And it's going to be pretty cool. So right, for max flow, we need a source and a sink, right? A sink. Here, it's not so clear. So what we do is, and this is like a common thing we do in every flow application. We like create the source and the sink. So what we're going to do is we're going to create a new source, S star, that's going to connect to all the factories, okay? And the intuition is like, how do the factories get their stuff? It came from that source S star. And now, right, some of the nodes are going to end up with excess flow, right? These red nodes, right? In this circulation problem, right, this node is going to have three things, right? That's the problem definition. To turn it into a flow problem, right, a max flow problem, that extra stuff has to go somewhere else, okay? So what we're going to do is we're going to add a new sink T star, and we're going to connect it to all the factories. And intuitively, all the excess flow that we want to route to those, to those red nodes is going to end up at T star, okay? So let's see a diagram. So the diagram is like this, right? So all these things are the original, input, and I just created some new nodes, S star and T star. And the intuition is right, like, how did this factory get 4 units of things? Well, it's like somehow S star sent it 4 units of things. How did this factory get 7 units of things? S star gave it 7 units. And now, right, this red node is going to have excess flow 3, right? That's the problem, right? I want to end up with 3 things here. But for a standard flow problem, right, I need flow in equals flow out. So I need to send those 3 things somewhere. So I'm going to send it to T star. Okay. And now the claim is that, right, any way to route things in the original graph that satisfies like the supply and the demand constraints corresponds to a feasible flow in this new graph, okay, where in equals out for every node. Does that make sense? Like, any comments, questions? How do we, any questions about how these new blue edges appeared? Yeah, happy to go back if you didn't understand the original problem. Yeah, I mean, feel free to ask questions. I mean, if it's obvious, that's fine, but okay. All right, so actually, yeah, can someone explain to me, like, why running max flow from this S star to the T star solves the original problem? Yeah. Yeah, so let me break down what your friend said. Essentially, one way to kind of concisely say that is like, if I go back to my original problem, oops, this is highlighted, but any way to route like 4 things here and 7 things here to 3 things here and 8 things here will correspond to a valid flow in this graph, right? If there's a way to do it, there's a way to do it in this graph, because this new source S star, right, and T star, right, I'll say, okay, find the maximum flow from S star to T star. If they saturate these 2 edges, right, that means they have to saturate these 2 edges, because 7 plus 4 is 8 plus 3, that's 11. So if they're saturating these 2 edges, that means S star is sending 4 units of stuff here. S star is sending 7 units of stuff here, right? That's how these factories get their things. And then the rest of the white nodes, right, it's flow in equals flow out, so they satisfy conservation. And now for these red nodes, right, they have to end up with excess demand, right? Because what they're doing is they're sending kind of this excess demand to T star. So in the original problem, right, they'll end up with some stuff stuck there. That's exactly what we wanted. Okay. Yeah. Yeah, so another way to say it is like these edges, new edges that we added, kind of capture either for the red nodes how much flow ends up getting stuck there, and hopefully it's equal to what we want, right? So that edge will be saturated. And for these green nodes, it captures how much stuff that originated from those nodes. All right. Yeah, and this is like a, seems like a pretty practical problem, right? Like, I have some stuff, I want to send it to places, whatever. And now, right, it's like, it's a very complicated problem, but if you know about flow, it's a simple application of it, okay? So that's one of the cool things about flow is like, anytime you're like solving some assignment problem, most of the time it's just a simple, you just have to reimagine what the graph is, and it's going to be a flow problem, okay? All right, any questions about this example before we move on? All right, so now let's study an even harder problem, okay? So now I'm going to introduce lower bound constraints. So what does that mean is, what that means is, I'm going to, for every edge, right, previously I had these capacity constraints that limited how much flow can go on those edges. But now I'm going to have a lower bound constraint saying at least some amount of flow must flow on every edge, okay? So this is a harder problem, right, because previously we could just send 0 flow. That'd be fine. But now I want to force at least some amount of flow to go on every edge, okay? All right, so this is an extension, extension. We want to lower bound, like for every edge, not only do I have an upper bound on how much things can go, I also have a lower bound saying at least L sub b must flow on every edge, okay? So now it's a harder problem, right? Like, just ignore the demand constraints. Let's say the demands are all 0 for now, right? That just means, let's just say even for the original, max flow setting that we talked about last time, if I say some amount of flow has to go on every edge, now it's like not so clear, like, right, what to do. Even finding a feasible flow, any flow that satisfies the lower bound constraints is not so clear. Because previously, right, in last class, there was always a trivial feasible flow, just send 0 from S to T. But now I'm saying, now actually I have lower bounds. Every edge must have some amount of flow going through it. And you know what, let me just also add in these demand constraints, right? As in the previous example, every node also has a demand, okay? So now this seems like a very hard problem, right? I have these lower bound constraints and these demand constraints. How can I solve this problem? Okay, so that's the problem that we're interested in, okay? So it's like I give you a graph, okay? I give you a graph. So let's go here. Like, I give you a graph. There's green nodes and red nodes and these white nodes. I have some amount of stuff I want to send from the green nodes to red nodes. But I have a constraint that for every edge, I give you a lower bound number saying at least that much flow must flow on that edge. Okay? So previously, right here, the capacity just means the lower bound was intuitively 0. Right? I could send 0 on any edge if I wanted to. And right, for this edge, I can't send more than 14, but I was happy to send 0. But if I had a lower bound of 5, then that means, at least 5 units of flow must flow here. Okay, so it's like a much harder problem because I'm constraining the solution a lot. Okay. Does the problem make sense? And like, do you see why it's an extension of the previous problem? Okay. Questions? All right. All right. So I'll have a drawing in a bit. But essentially, if I tell you that some amount of flow must go on every edge, then the first thing that we can start with is saying, okay, I know that for every edge I have this lower bound. I'm going to start by putting that much flow on that edge. Okay, so that seems like a very natural strategy to try. Okay. So the first thing that we do is we say, okay, I'm going to define this initial flow, F0, that says, okay, the problem tells me there's a lower bound on the edges, so let me just put that much on every edge, okay? Of course, that might not satisfy these demand constraints, okay? So we have to fix that. But at least that will satisfy this capacity constraint, right? If I initially say, okay, on every edge, I'm going to start out by putting this L sub b. It may also not satisfy like conservation, right? Because I'm just starting by putting some things on every edge. It may not be that flow in equals flow out. Or it may not be that these demand constraints are satisfied yet. Okay, so we have to fix that. But at least if I define this initial flow by putting the lower bound value on every edge, that will satisfy the lower bound constraint. Okay. Does that make sense? Like, don't read the rest of the thing. Just like just the first part, which is if I put the L sub b flow on every edge, that will satisfy the lower bound constraint. Okay. And now the way I fix the demand constraints is saying, well, I start out by putting some stuff on every edge. That's going to change the demands, okay? What that means is, actually, right, if a node said, okay, I demand 5 units of flow to stay with me at the end, right? It's one of those red nodes. And I start by initially putting some flow on every edge. Then the demands are going to be changed, right? Because I already have some initial flow going to every edge. So let me quickly give an example, okay? Let's say this is my original input, okay? I have some green nodes that have some stuff to send. I have some red nodes that want some stuff. And I have these capacity constraints, okay? And let's just say I only have a lower bound for this edge. This edge must have 1 unit of flow going through it. The rest can have 0. Then what do I do, right? I start by putting 1 unit of flow on that edge. Okay, that at least satisfies the lower bound constraint. But so what does that mean, right? That means intuitively I'm sending 1 unit of stuff from here to here. Okay. That means this node actually has less stuff, and this node ends up with more stuff. So what that means is if we transform the graph by forcing whatever the lower bound is on every edge, then then our problem with lower bounds actually transforms into the first application where we only have demands and that's applied. Okay. So that's what this slide is saying, right? If I force some L sub E flow on every edge, then the capacity changes, right? Previously, it was like L sub E is less than or equal to F sub E, less than or equal to the C sub E value, right? The capacity on every edge. If I force every edge to have L sub E flow, then of course I don't have a lower bound anymore. I'm happy, I satisfy that. But the capacity is also reduced. So the graph changes. And I'm saying, well, the graph changes in one more way. The demand constraints change. Because I'm sending something on every edge, actually some stuff will end up accumulating on some nodes, and some stuff will end up leaving some stuff on some nodes, just because I forced every edge to have whatever flow. So if that didn't make sense, let's again take a look at this example, right? If the only lower bound was on this edge, and I forced 1 unit of flow to go here, then it will be, this -2 gets turned into -1, because 1 unit of stuff is going to leave, but then more stuff is going to end up here. Does this example make sense? So yeah, it's like I'm just saying like a ton of words, but the idea is super simple. It's just, if I force some things on some edges, it's going to change some demands and some supplies. Yeah. Yeah, exactly. That's the whole point, right? Yeah, that's why algorithms are powerful, because if we solve one problem, we can turn other problems into example problems, right? So yeah, that's pretty much what's happening here, right? I have some, annoyingly, I have some lower bound constraints. What I do is I pretend they don't exist by shifting some stuff, and then it transforms, right? Then I draw a new graph, which is essentially this supply-demand problem with no lower bounds, which we just saw how to solve. Okay. So that's why that's why I talked about this term reduction in the beginning, right? We started with a seemingly difficult problem, but we say, it's actually this other problem in disguise if we transform it a bit. Yeah. Yeah. So if that didn't make sense, just at a high level, just think, if I give you these lower bound constraints, there's a way to transform it so that it turns into the previous problem. Yeah. Yeah, exactly, right? So that'll definitely be the case, but that's why we alter the demand constraints now, right? Right. Let's say previously I was, one of these intermediate nodes, right? I didn't want any demand to come to me, okay? But then let's say only this edge had a lower bound, okay? So then to kind of get rid of the lower bound, I forced 1 unit of flow to go from here to here, okay? But then this edge ended up with the extra surplus, right? But now to transform to the original problem, what I would do is I would say, actually, this node is a green node with one thing that needs to send it out. Yeah. Yeah, exactly. Yeah. Uh, right. So in this previous example, right, here I'm saying, what does the lower bound of 1 mean? That means I had to force at least 1 unit of flow to go here. That was part of the input problem. Previously, right, in all the flow problems we talked about, you could put 0 things on an edge, right? You'd be happy. So how do I transform this, this setting where I have to force 1 thing to a setting where I'm happy with 0? Well, by like kind of sneakily putting in 1 unit already. If I put 1 unit of flow already on that edge, and I pretend it doesn't exist, okay? So at the end, I have to add that back in. If I just sneakily put 1 unit of flow here and pretend it doesn't exist, then what I'm doing is I'm kind of effectively getting rid of the lower bound, saying that previously I had to force 1 unit of things here. I already put that thing there, so then I'll be happy with 0 if needed. But then the capacity changes because secretly I'm already putting 1 unit of flow there. And then the demands also changes because, right, here if I put 1 unit of flow, then this node ends up with more stuff. So the demands become a little bit different. So you have to like redraw the graph and redo the supply and demands, right? Because some things might end up accumulating, but to solve our original problem, right, we might have to like alter these demand values by kind of saying, if some, so like here, right? Here I'm saying I'm going to solve the supply-demand problem without lower bounds with this new value of -4. If I solve that, that actually, by kind of adding back in this 1 unit of flow, that actually solves the original problem that I care about. Okay, so that's all I'm saying. But again, if that didn't make sense, like just the high-level takeaway point is this new problem with lower bounds is actually this old problem in disguise if I cleverly manipulate the input. Okay. Okay. Yeah. So at a high level, what's happening is like, okay, I'm gonna subtract this capacity from every edge, right? I'm gonna pretend that edge already gets that much of flow. I need to alter the demands, and then then I get a new graph. And on this new graph, I solve the old problem, right, which is just the supply-demand problem, the circulation problem. And now to go back to the problem I care about, I have to add back in these things I added. Okay, that's all that's happening. So but if that didn't make sense, like just think, what is the ultimate tool that we end up with? The ultimate tool that we end up with is like a more powerful version of max flow. So previously, right, we could only solve max flow, but now we can solve the following more general problem, right? I give you a graph, I give you a lower bound on every edge, I give you an upper bound on every edge, right? That's the capacity, and I give you a demand for every node. Okay, so this is a more juiced up version. And then the problem that we can solve is find any feasible flow that respects the lower bound and upper bound constraints and also respects the demand constraints. Okay. So if I just told you this like, maybe last class I say, okay, I told you this like more advanced version, you say, okay, this seems much harder than flow. But actually, it turns out, if I just change the graph a bit, right, then I turn this problem into the, into the circulation problem, which we turn into the flow problem. Okay. But yeah, just if that didn't make sense, just think. We have a way to solve this more meta problem. Okay. That's all. Okay. Any questions so far? Right. So I just showed you, right, 2 examples of harder problems or seemingly harder problems where if I change the graph, I add some new nodes, whatever, they end up just being applications of flow. Okay. All right. Yeah, and if this seems a little bit hard, like I would say, do the homework for this week, or that was posted last week, and kind of that is kind of what I'm expecting of you in the exam, right? It's not just like prove something about the flow. It's more like solve this problem using flow, right? So you probably have to, for instance, the first problem is about supplying blood or something, right? And that's a matching problem in disguise. So if you can, if you can understand how to solve that, then that's kind of what's going to be on the test. Okay. All right. So this is also like a cool example of like combining. If I know how to solve one problem and I know how to solve another problem, right? It kind of chains together, and you end up being able to solve harder and harder problems. Okay. So that's the nice thing about having a tool like Flow. All right. So now let's see one more application that's actually really cool, and it's more concrete. Okay. And then the next half of the class, we're going to talk about another way to find maximum flow. Okay. That doesn't have this F dependency that Ford Fulkerson does. All right. And you might say, okay, why did the style of the slides change? Like, I just found this online, so I thought it was a pretty cool application. Okay, so let me explain the problem. Okay, so I gave you a table of numbers. Okay, and these are just like real numbers, and they have a row sum and a column sum. Okay, what I want to do is say, okay, I want to publish these numbers, but I want the numbers, having like decimals is not so nice. So I want to publish whole numbers. Okay, round numbers. So I want to round down these numbers. Okay, so I want to round them either up or down. That's my choice. And now, what do I want to guarantee, right? So I want to round up and down, and I also want to round the row sums up and down. Okay, and that's that's up to you. But what do I want to ensure is that I want to ensure that the table is like consistent. Okay, so what that means is, if I round up or down, if I take the rounded version, right? If I round the row values, and I round the sums, in a way, they have to correspond to a table that makes sense. So that means, the sums, the rounded sums, are going to be equal. If I sum the rounded values, that's going to be equal to the rounded sum. Okay. All right. Does that make sense? So it's not just like I'm not just like rounding down these numbers. I also, another way to say is, I also want the row sums and the column sum to be off by less than 1. Okay. And yeah, and one application. I mean, I don't know if they still do this, but like if you look at actually, there's a big controversy with the 2022 census. 2020 census, by the way. But anyways, so one thing that you notice is like, it's not like they give you the number of, like if I say how many people live in Dane County, they essentially don't give you up to the single person. They kind of round it down, or round it up. But they need to do it in a way that's like consistent, right? In the sense that, they round up or down the value of every county, but then they give you a count for the entire state. And if I sum the rounded things for every county, it better be that that's like equal to the rounded value of the original state number. Okay. So the hard part about this is, if you keep rounding at the lower levels, at the top level you might end up with a huge error. Okay. So for example, right, let's say I rounded down everything, then like this sum would not, this sum would not correspond to this original value rounded up or down. Okay. Does the problem make sense? Questions? And the thing is, like, it's not even clear if there is a way to do this. Okay, like how can I round the values up or down so that if I sum the rounded values, that's going to be equal to the rounded sum up or down. It's not even clear if there's a way to do this. Okay. But the cool thing is, it's always possible to do this consistent rounding if I give you a table of numbers. Okay. And the way we're going to prove that is we're going to show it's actually max flow in disguise. We're going to find a feasible flow. And if I find a feasible flow, I know it has to be a flow that with integer values. I'll show in a second. And that proves that there's a way to do this. Okay, so it's pretty cool. And yeah, just one natural thing is like, okay, I don't care about the numbers. What I do is I just like look at the original tables and I like say, okay, if they're less than 1/2, I'd go down. Right, if the decimal is less than 1/2, or if it's more than 1/2, I round up. So if you did that, all of these things would be rounded to 0. Okay, but then like that wouldn't correspond to 1 rounded up or down. Okay. All right, so this naive algorithm doesn't quite work. Okay. Okay, so does everybody understand the problem, what we're trying to solve? Okay, so, all right, so now let's just see. Okay, so okay, so now we have to make a graph. Okay, so let me walk you through it. Okay, so it's going to be a max flow, it's going to be a flow graph. We're going to have a source and a sink, okay? All right. And now we're going to have an upper bound and a lower bound. So that's why we talked about this previously. Oh, actually, let me talk about the vertices first, okay? We're going to have a vertex for every row, and we're going to have a vertex for every column, okay? And essentially, right, I know what the row sums I need are, right? I need the row sum of this to be between 17 and 18, right? I need the row sum here to be between 12 and 13, right? Because I need to round up or down. I need the row sum here to be 11 or 12. Similarly, I know what the column sums I need are, right? I need the column sum of the first column to be between 16 and 17, and so on. And then, right, the rows and columns interact with each other. So for instance, what does this mean? Well, this means, right, this value that's in row 1 and column 1, it better be between 3 and 4. Okay, so these are the upper and lower bound constraints. All right. And now the only thing I do is I say, okay, is there a feasible flow in this graph? Okay. That satisfies the upper and lower bound constraints. Okay. And the reason why any feasible flow, okay, and the claim is like any sort of, okay, oops. Yeah, so let's break this down. Okay, so right, so I define a graph. Let's stop there for now. Does everyone understand like why the graph was defined this way, like intuitively, where all the numbers and the edges are coming from? Okay. And now the point is, right, well, now the problem is find any flow that respects the upper and lower bounds, okay? And that's essentially the problem that we saw last time, okay? Like that we just talked about. And now the claim is that if I look at the original table, like forget about rounding up or down, then that's a feasible flow, okay? That gives me a feasible flow. Why? Well, it's saying, well, what do I do for this entry? I put flow 3.14 on here. What do I do for this edge? Well, I put 17.24, right? That satisfies the upper and lower bound, okay? So that's a feasible flow on this graph, okay? All right? And then this is the really interesting part, which is, well, I know there's a feasible flow, and like, right, at the end of the day, like all these problems, right, they're going to be reducing to max flow. And we know for max flow, right, if there's a feasible flow, there's one that has integer values, okay? That's what the Ford-Fulkerson algorithm guarantees. So essentially, what that means is if I take this input and I run it through the algorithm from the previous part, it's going to give me a flow that satisfies the upper and lower bounds, and it's going to have integer values on the edges. Okay. And if I have, like integer values, that means I'm rounding, and I know that it satisfies the upper and lower bound constraints, right? So I'm rounding up or down. Okay. So that's the end. Yeah, so kind of what happened was that I encoded this problem as a flow problem, but I needed upper and lower bounds. Then I said the original table actually gives me a feasible flow, right? But the flow has like real numbers, right? It has like decimal numbers. But I know, right, if there is a feasible flow, there is a flow that has at least that much value, right? Or like, in other words, if there's a feasible flow, there has to be a flow that's only only uses integers, okay? And if there's a flow that only uses integers and it satisfies the upper and lower bound, then that exactly corresponds to the rounding that I want. Okay, so essentially, like, somehow this helped us. Like, the hard part was making sure everything was a whole number, right? It's same in the matching example, right? Like I want to match every student to one item of clothing, right? Maybe you can think, okay, if I give someone fractional, like if someone gets half a hat and half a shirt, I can pretend there's a matching. But the magic part about flow is like, if I show you any feasible thing, then I automatically know there's a, as long as the capacities, right, these upper and lower bounds are integers, I automatically know there's a integer version as well. Okay. So yeah, that's it for this application. So what this actually shows, right, not only does this give you a way to round, so what you do is you just run, okay, I mean, I didn't tell you the, the supply and demand. You can say every intermediate vertex has supply and demand 0, and this has, like, let's say, yeah, I guess supply, that's the sum, demand, that's the sum, whatever, you can play around with it. But what might go? Yeah. But yeah, I guess I just wanted to show you, like, oh yeah, that's what I was doing. Right, when I told you this problem, it wasn't even clear that it's possible to do this rounding, okay? So not only does this prove to you that if I give you any table, it doesn't have to be a 2D table, by the way. Any, like, 3D table, right? You can imagine any statistic, right? Like not only do you have, like, population by, going back to the census example, right? They don't just record who lives there, right? They record how old you are, what your education background is, maybe how much money you make, all these numbers, I'm saying, like, there's a way to round all these things up or down so that the sums are consistent, okay? But just let's focus on the 2D case, right? If I give you an n by n table, that's, like, huge. It's, like, not so clear how to round up or down. So this actually proves that not only is it possible, but it gives you a way to do it, okay? All right. Okay. Yeah. Yeah, so all of them have upper and lower bounds. I just didn't write it down. So I guess all I'm saying is, like, right, so these every edge has an upper and lower, right? So this entry has a 3 and 4 because it's like, I want to round it to 3 or 4. But this edge, right, has a 2 and 3, right, because I want to round 2 up or down. And I'm saying there is a feasible flow on this graph, okay? Which is I just look at the table and I send that much flow on every edge. That's feasible, clearly, right? And if I know there's a feasible flow, there must be an integer feasible flow. Okay. And the way we prove that is, well, this problem is just a max flow problem in disguise. If we know for max flow, right, if there's a max flow of a certain value, there's an integer max flow. But this is like just a feasibility problem, so it turns out that logic also applies. There's a integrality theorem. Essentially, it means I can always round things to be integers. Like you can imagine, right, if I take this problem and I run it through all the reductions that we talked about, how would I solve it? Well, I would solve it using Ford-Fulkerson. That will end up giving me an integer flow. Okay. All right. But the kind of the high level takeaway here is that these lower bound constraints, which I didn't show for these edges, right, upper and lower bound constraints, they actually capture something about the problem, and they enforce something non-trivial, okay? And just like for this problem, right, it just happened to be that we formulated this way, but you can imagine, other problems where, like, I must send something on this edge, or at most this many things on this edge. Like that kind of problem, you can solve with flow, okay? That's the high level takeaway. Probably, like, you won't see a lower bound example on the homework and in the test, but I just wanted to show you because it's just like a cool fact, right, that you can always round in this way. Okay. All right. Now let's transition to the other part, the Edmonds-Karp algorithm. And again, it's like a more advanced algorithm for finding max flow. So now, don't remember anything we just talked about, right? Now we're in the previous setting where I have a source and a sink, and I just want to find the maximum amount of stuff to go from S to T. So this is an alternative to the Ford-Fulkerson. Is an alternative for Fulkerson, mainly because like Ford Fulkerson has a running time that's not so nice, right? It depends on this f parameter. This algorithm has no dependency on the values on the edges, right? It will always give you a max flow, even if the values are real numbers. The capacities end up being, some fractional number. This will work, okay? And yet, probably this won't be in the homework or exam because it's just like, like I said, the type of questions we'll ask is just apply flow to a new example. But it's still pretty nice to know, okay? So again, right, what is this? Right, I introduced like so many different variants, so let's go back to the most basic variant. I just have a graph, right, and I just have a source and a sink, and I want to, and there's no lower bound constraints, okay? It's like the previous setting from last class. I just want to send as much flow from S to T, okay? So it's the max flow, the original max flow problem. And this algorithm runs in m squared n time, no matter what the values are on the edges, okay? Even if the capacities are arbitrary real numbers, it will still give you a maximum flow in m squared n time, okay? It doesn't depend on the, kind of like, when we sort numbers, right? It doesn't depend on what the values are. It's an n log n time. It's kind of the same here. As long as I can compare two numbers, I can get m squared n time, okay? Yeah, actually, this is a little bit too hard for this class, so I'm going to show a slightly worse version. But if you ever need it, like, then you just know that max flow, you can find it in polynomial time, m squared n time, okay? Yeah. And the main idea is, right, previously, how do we find a max flow, right? We had this, residual graph G sub f, and we said, okay, as long as I can find any path connecting S to T, then I can send some flow on it. But now instead, we're going to say, okay, actually, I want to find the best path to send from flow from S to T. So what that means is I'm going to select these augmenting paths in a slightly smarter way, and it's going to lead me to a faster algorithm, right? If I send more flow, then I need less, then the algorithm becomes much faster, right? It finishes faster. All right, so for this particular lecture, we're going to still pretend all the capacities are like whole numbers, integers, but as I said, the full version of Edmonds-Karp doesn't need that assumption. But if we assume the capacities are integers, then previously for Fulkerson run in time m times f, but now essentially we're going to get a time that's m times log f. Okay, so it actually goes from f to log f, so it becomes a lot faster. So if the max flow value is 10 million, previously for Fulkerson could take 10 million steps, but now this algorithm will take 6 steps. Okay, log goes a lot slower. Okay. All right. So like I said, in for Fulkerson, we picked an arbitrary augmenting path, right? As long as we could send some flow from S to T, we were happy. But now we're going to pick the paths in a slightly smarter way. Instead, what we're going to do is, add an intermediate step, right? Instead of finding any path from S to T, we're going to find the path that allows us to send the most unit of flow from S to T. So it's not so clear how to find it, but let's pretend we can do that, okay, for now. Essentially, that's the only change. Okay, so that's the only change, okay? So I still have to show you how to find the largest, the best path. But that's the only change. Instead of finding an arbitrary path, right, using DFS, we're going to find the best path. Okay. Questions? Right, intuitively what's happening is, right, we're making more progress because we're going to send, previously in for Fulkerson, all we could guarantee was at every iteration the flow increases by value 1. But now we're going to try to push as much from S to T as possible. And hopefully it's going to finish a lot faster, okay? All right, so that's essentially the whole the algorithm, just one change, okay? But the analysis becomes a lot. It actually becomes much simpler, actually. So that's pretty cool. Okay. All right. So at some point we need to say, okay, how much flow can I send at every stage, right? Previously, for Fulkerson, the only guarantee I had was I send at least 1 unit of flow, right? So that's why I took f iterations. But now the claim is the following, right? If I somehow magically find the best path from S to T, then I can I can send actually a little bit, I can send a lot more, okay? So the way I quantify that is say, let's say in the very first round, very first iteration, okay? Forget about the intermediate rounds, but even the very first step, right? Like I said previously, I could only guarantee 1 unit of flow. But now the claim is that even in the very first step, if the final value is f, I can send at least f over m units of flow if I pick the best path, okay? That's the claim, okay? And it kind of makes sense, right? Like, hopefully this is much bigger than 1, so then I'm making like progress faster, okay? So why is this true? Any idea, intuition? So okay, so I'll show you the proof, but the idea is following, right? What does big F mean, right? Big F means, it means there is some way to send F units of flow from S to T, right? How many edges are there? There's at most M edges, right? So intuitively, like, you know, some edge is going to have a lot of flow, right, on the best way, right? F over M, right, by, you know, some sort of averaging, right? So that's kind of the idea. But the kind of the clean way to prove is as follows. What we do is we say, okay, the way we're going to show that there's a like, you know, there's an augmenting path is, well, I'm going to delete all the yeah, so let me, right. So yeah, so what's going to happen is if I delete all the edges with capacity less than f over m, there's at most, you know, there are only m on the edges, right? And so I couldn't have disconnected S and T, okay? I couldn't have disconnected S and T because even in the worst case, all the m edges participate in this, okay? All the m edges get deleted, but the amount of capacity that I've deleted is less than f, okay? But I know the flow is f, right? I know the max flow is f, so I know the min cut is also f, okay? So that means, like, you know, I have found if I've disconnected them, then I've found a cut with value less than f, which is not allowed, okay? So that means S and T are still connected if I delete all these small edges. That means there is a path from S to T. Oh yeah, so it's a little bit tricky. But yeah, so let me run this again, right? So what do I want to show, right? Actually, let me not show this. I want to show that, you know, if the flow value is large, there is a path from S to T that I can send this much flow on. What that means is, right, it's enough to show there's a path from S to T where all the edges have flow, have capacity at least f over m, okay? If I have that, then I'm good, right? Then I can send f over m flow on that path. Well, to show the existence of that path, what I do is I delete all the edges that are not nice, that I don't want. And then, right, I still know S and T are still connected, okay? Because, right, if they were not connected, then I found a cut of size less than f, which violates the max flow min cut theorem. So that means if I delete all the edges with capacity less than f over m, then S and T are still connected. That means there is a path from S to T that uses only edges at least f over m. That means I can send flow at least f over m. Okay. If that didn't make sense, just think like, okay, if the flow is large, there's a way to send a ton of stuff on some path. Okay. But yeah, if that kind of makes sense, like, but some part didn't, please ask something. Questions? Okay. All right. So the idea is, like, if there is some way to send a ton of flow, always, then if I keep picking that way, then I'm going to make progress really fast, okay? In particular, it's going to be the case that, like, right, previously, how many iterations did for focus intake? It took big F iterations. But now it's going to take it's going to take m log f iterations. Okay, if I keep sending stuff on this, super awesome path that can send lots of flow. I mean, essentially the idea is we keep applying this statement, this previous statement, over and over again, right? Right. Essentially, what's happening is that, right, in some intermediate step, let's say the flow left over that I can send on this graph is f prime, right? Initially, it's big F, but then, right, I keep sending more and more stuff, right? So f decreases. But I know at every point, right, the previous thing guarantees that the stuff that I can send is f prime over m, whatever f prime is the intermediate stuff, an intermediate value of the flow. So what's happening is, like, at every iteration, the flow that I have left to send over is decreasing by this factor. Okay, that's the high level idea, right? Another way to say it is whatever flow I have left that I can possibly send from S to T, there's always going to be a way to send at least that over m units of flow on some path. So that means the flow that's remaining as I keep running through different iterations is decreasing by this factor, 1 minus 1 over m. And the question is, like, how many times can I multiply 1 minus 1 over m to f, right? At some point, it's going to be less than 1. If I assume everything is an integer, if it's less than 1, then it must be 0. So this is the calculation. Oh, sorry. This should be f, not f prime. So essentially, I'm saying, right, initially I have f flow. At every iteration, I'm guaranteed to decrease it by a factor of 1 minus 1 over m. Okay, it's a small factor, but it's still a multiplicative factor. And how many times can I do it until it becomes less than 1? Well, if you solve this, it's roughly m log f. Okay. And, like, how do you know this? Well, it's like you can play around with it, or you can say, okay, 1 minus 1 over x, 1 minus x is roughly e to the negative x, right? That's like Taylor, I shouldn't use x. 1 minus 1 over m is roughly e to the minus 1 over m. Okay, this is using the Taylor series. So it's e to the negative x over m. What does x have to be to cancel this f? It needs this m factor to cancel this m, and it needs the log factor to get rid of the e. Okay. So the high-level takeaway is, like, if I keep sending flow on the most, the best path, it's decreasing by a multiplicative number, and that's why I'm getting this log term, because it can only decrease so much until it becomes 0. Okay. All right. So kind of the takeaway point is, if I keep doing this, like, find the best augmenting path, then the number of iterations goes from f to roughly m log f. So the f dependency, right? F is huge because it depends on the numbers, right? The graph can be small, but if the numbers are large, the forward focus takes a really long time, which doesn't really make sense. Here, here is kind of scaling with the graph in a nicer way. Okay, it has an m dependency, but a log f dependency. So if I put a 10 million on an edge, it's not going to take 10 million steps. It's going to take like 7 or 8 steps. Okay. All right. So now the question is, how do I find this best augmenting path? Okay, the path that allows me to send the most unit of flow. Okay. Turns out it's the same as Dijkstra's algorithm. Kind of the intuition is, like, right, the thing we need, right, on a path is we're not adding up the edge lengths, right, in Dijkstra's algorithm. We're taking the minimum, because whatever the minimum is, that's the amount of flow that we can send on the path. So essentially what we do is we run Dijkstra's algorithm, but instead of, like, replacing with the sum, we do this minimum trick. Kind of the same trick that we did in minimum spanning tree. Okay. So how do we find the largest capacity path? Well, right, we have a source, which is the S node, right? We want to find the largest capacity path from S to T. The way we do this is the way we find the largest capacity path from S to all the nodes. Okay. What do we do is we maintain a tree, just like the Dijkstra's algorithm. So let me just show you the main loop. Okay. So this is all like pre-processing, and you say, okay, we're going to pop some vertices like Dijkstra's algorithm. But instead of, like, popping by the minimum, like, in Dijkstra's algorithm, we pop by the distance, right? Distance to the source. here we're going to say we're going to pop by the minimum capacity value, right? It's just a number, right? We can pop by it. So let me just show you the main loop, right? Every time we pop actually, let me show you the entire thing. So every time we pop a vertex, right, instead of popping by the shortest path, we pop by the highest C value, the capacity values, and then that lets us reach more nodes, and then we update the capacity values of those nodes, right? And, here, right, there's no sum, right? Instead, we have to do the minimum on the path. So I'm saying every time I pop this V, right, or anyways, every time I pop a new node, it lets me reach more nodes. So I loop over those edges that I can reach, and I have to update some things for the endpoints, right? Which is, well, I got to that node V through U, so then it better be like the minimum of the, capacity that I need to go to U, and like I need to take this edge, so I need to take the minimum. But then, right, I take the best path to that vertex. Okay, so essentially it's the same logic as Dijkstra's algorithm, right? The only difference is I'm not keeping track of like the sum of the shortest paths, right? Previously, I was saying the minimum of all the shortest paths that can go through that. Like every time I discover a new frontier, I'm updating on the shortest path. Here, every time I discover a new frontier, I'm updating on the capacity values. But right, I care about the maximum capacity, right? Not the minimum shortest paths. Okay, so that's why the max and the mins are that way. But essentially, it's Dijkstra's algorithm. Okay. Yeah, and if I run Dijkstra's algorithm, right, it takes m log n time if I use a heap. And we know previously, right, it has m log f iterations, right? If I find the best augmenting path every time, I'll be done after m log f steps. So then if I put those two runtimes, together, then this version of the Edmonds carp that I showed you, which only works for the integer values, by the way, right? Because I'm using the fact that things, as long as things become less than 1, it becomes 0. Then the total runtime would be roughly m squared log f. And previously, right, for the Fulkerson was mf. So in some cases, if the values f are really big, then this is a better choice. In general, there's like a different version of the Edmonds carp that works for like non-integer values, and it takes m squared n time. So it has no f dependency, right? Because essentially you can even handle like arbitrary numbers. But it has like one more advanced kind of idea that I didn't want to talk about. Okay. But yeah, I know I went too a little bit fast, but yeah, any questions about like, at least at a high level, like why Edmonds carp made progress, how we found the best augmenting path. Yeah. No, this is it. Yeah, because there is no need for an example, right? Like there's two steps. One is if I abstract away how I find the augmenting path, right? Then let's just like right. If I just say, okay, someone magically tells me the highest capacity augmenting path, then we showed how many steps it takes, right? And the question is, how do I find the highest augmenting path? And my claim is that this is actually just Dijkstra's problem, except the way I define shortest paths is different. The way I define shortest path is not the sum of the edges on a path. It's the minimum value that I see. Okay, so I'm defining shortest paths as not as a sum, but the minimum value. And you can think it's like, right here. Actually, let me show you why. Let me go on the board. Okay. Yeah. That might make it easier. Yeah, that's the nice thing, right? So if you understand how Dijkstra's works, then okay, these markers are bad. All right, I'm gonna use Okay. All right. Okay. I'm going to have to write this thin pen. Okay. All I'm saying is it's exactly the shortest path problem, except I'm defining the, right? So previously, right, what is the cost of a path, right? Cost equals sum of the edge weights, okay? That was the previous, okay? That's the Dijkstra's. Now, what I'm saying is the cost of a path is not the sum, but I take the essentially the weights are the, right? Previously I called them weights. Now I don't have weights, right? Now I have capacities. But it's the minimum on that path, right? The cost of a path is, right? Previously it was E in the path. But now it's minimum of E in the path. Instead of summing them, right, I just take the minimum, okay? So let's just start with this change, right? Why is this, let's say this is the only change I make in the Dijkstra's, in Dijkstra's. All this means is like, previously in Dijkstra's, we did this relaxation step, right? Where we say, okay, when we go to a frontier, right, we're at some V, and like that was just popped. It has some edges, right? How do we update the values for those edges? We say, okay, whatever it was for those, I say, okay, oh, those edges are taking, the values are too large. To go to that node, instead I can go to V, use that edge, and shortcut it, okay? And the way I said was, okay, and then I replace, like, if I have edge VU, the way I replace the value of U is I take the value of V plus that edge. But instead of doing the plus, I'm going to say, right, if I discover a node V and I say, okay, now what do I do for U? Well, I say I look at the, the value for U. I say, well, one way to get to U, right, is go through V and take this edge. Previously, I said this plus this. Well, now I say minimum of this and this. Okay, so I'm just changing the plus step to a minimum step. Okay. So I'm still like popping these values, right? I'm still popping like these. I call them. I think I call them priority, right? Priority values. Except I'm just changing the update step, right? Instead of updating the priorities to be, right, if I go from V to U, right? Previously it was, well, the priority for U, or the value for U, better not be bigger than V plus this edge. But I'm saying the priority for U better not be the minimum to get to V and the minimum of this edge. Okay? Because I don't want the sum of the paths. I want to know what the minimum edge is on the path. Okay? So that's fine. And now, yeah, so that's the only change I made, right? Like, and let's see. And yeah, so actually, like essentially this is the same thing as we did for. So if you look back to minimum spanning tree, right? That also used the Dijkstra, right? Because we wanted to find what is the cheapest way to connect the tree to the rest of the unconnected vertices. We wanted the smallest edge weight. It's actually the same. Okay. So yeah, there's no. I didn't prepare an example, but yeah, it's just Dijkstra's algorithm. Okay. Questions? Yeah, but maybe I'll link a set of notes where it'll go through a series of examples if you're interested for Edmonds Carp. But yeah, it's not going to be covered in an exam. It was just like a extra interesting max flow algorithm. Questions? Okay. All right then. Yeah. See you next time.